We were able to hear from a lot of professionals and experts on underwater communication. So I would like to briefly go over just the big picture of what exactly is underwater IoT.
And so this page shows the content of my presentation. The first one is the why underwater communication we need. Next one is, and then, so how to do it. And so the next one, I defined the new the concept of IoT. Actually, the way you think about the IoT, that is just for some IoT system in terrestrial, actually based on the high RF signal. But however, in the future, we need the new definition of the IoT systems, including underwater IoT. And so the next part is the future plan of underwater IoT. Finally, I summarize the standardization for underwater communication technology. As the first one, actually, I've already mentioned in the form of this session, the Earth is covered with the water. Over the 70% of the Earth's surface is water. And then, so the why underwater communication? Actually, so we have the lots of some of the application domains, and we need, for example, resource, the resource exploration as ecosystem, the energy harvesting, and so on. So we have a lot of some of the application domains. And this page shows some of the market. Actually, so this figure explains us that the underwater wireless communication market is growing 18.5% every year from 2016 to 2022. And so this figure shows the fire ice. Actually, this is called some the methane, the hydrate. That means this is some kinds of some the solid methane. This is located under in the East Sea. And so maybe somebody says the Dokdo. Actually, Dokdo is the big issues. And so that means that Japan would like to find the capture the kinds of the fire ice under the Dokdo. And then the next one. However, this is the irony. We know more about the surface of the Mars, the Moon, the Venus, and the depths of ocean. And then that 95% of the ocean is unexplored. Amazing one. Actually, we don't know about the 95% of the deep sea. We don't know. And why? Actually, the first problem is that it's very difficult to access due to extreme, the high underwater pressure. As you know, the air pressure here is just 1 bar. But however, every 10 meter in underwater, and so the increase is the 1 bar. That means if we are going to some 100 meter under the sea, and so the water pressure is at 10 bar. It's very amazing one. And then the next one. So we do not have any way to communicate in underwater. That means that the limited communication way in underwater. So how communication? How communicate in underwater? Actually, so as first the diver, they using the kinds of some the sign language by using the hand. And then so the other one is so the one of the best way for communication in underwater. Actually, we have to use the ultrasonic signal as the Yongjin, working group 5 explained to us. Actually, so the propagation speed of the ultrasonic is just 1.5 kilometers per second. That means we cannot use the legacy communication protocols that are based on the TCP IP. And so we have to create the new the protocols, underwater protocols like this one. And however, we have several the application domains. This one shows some diver phone. That is based on the acoustic, those solutions from Japan, United States, and Italy. And then next one is the diver computer. And so this is called the diver watch. If you are interested in the diving, and then maybe you have this kind of the diver watch. So that is from the Korea and Finland. Actually, so the Sunto is the best seller in these areas, and so the United States and German. As I have to skip these video clips, and then next one. So as I mentioned, so we have the large of, actually the 4 communication methods in underwater. The first one is the acoustic, actually it's the ultrasonic signal. Maybe you can see some of the movies. The dolphin can communicate each other by using this kinds of the ultrasonic signals. The human, imitate or the mimic the kinds of the nature phenomena. So by using the ultrasonic or the acoustic signals, and this is one of the popular communication methods in underwater systems. And then, but as Yongjin mentioned, we have several limitations when we are using ultrasonic signals. Because of that, now we have another new candidates, technologies for underwater communication, such as optical or the low frequency, and so the MFAN or the MI. MFAN stands for the magnetic field area network, as MI for the magnetic induction. And the last one is the infrared. So actually, we can use the several bands, IR, UV, the ultraviolet, and so the blue, and the red or the green band in the visual light. And so this page shows the examples of the VLF or the ELF communication. Actually, this kind of the communication is used in the submarine communication. Next one shows the legacy, the underwater communication systems, mainly based on the acoustic communication. But as I mentioned, we have several limitations. And so this is the new or the future underwater communication systems, including acoustic, visual light, the MFAN, the low frequency, and the infrared communications. This one shows us the examples of the product from Sonadyne. This is one of the best solutions for the underwater communication by using the visual light communication. And so this one is done by the Kookmin University. Actually, that is the UHSTM, the LSAD, the MMMB. MMMB stands for the multimedia and the multiband. So the Kookmin University actually invented this kind of the MMMB system. And so that is called the UHSTM, stands for the underwater hybrid software-defined modem. Actually, this system is applied to the diver network, the advanced diver network, ADN. So we are using the visual light, blue and red. And so the blue, red, and some the infrared communications. But in this system, we do not include some the IR communication, not yet. So this page explains the extreme low frequency and the very low frequency. And then the last one is the MFAN, the magnetic field area network. This is the MFAN, the standards is always done in S6 by the KETI, the KETI in Korean, some institute. And so next one shows the comparison between some the current technology, acoustic, optical, magnetic, and low frequency from the viewpoint of the several metrics. For example, so bandwidth, attenuation, latency, and so on. And this page shows the new concept. As I mentioned, nowadays, when you define the IoT, we don't need to call the IoT. Actually, that is called the TIoT. TIoT stands for the terrestrial IoT. The legacy IoT is this one. But however, from now on, the underwater IoT should be included the definition of the IoT. So this figure shows the concept of the IoT. And then next one is that the IoT architectural framework. As you know, when we think of some of the IoT systems, we have the SPND. S stands for the service or the content. P, platform. C, the N stands for some connectivity, including the backbone network, and so the edge network or the edge networks. And then finally is the device. This figure shows some of the underwater architecture, the framework based on the SP&D concept. Next one is the how to integrate the TIoT and the UIoT. As the Wang Chen, the working group for Kookmin, said, the integration is very important issues in the IoT systems. Actually, as for us, we have new solutions, how to integrate the legacy, the TIoT and the UIoT in order to build the 6G network systems. And then that means that we have to specify some new systems for the backhaul in these 6 systems to support integration of the TIoT and the UIoT. This figure shows the future plan of the underwater IoT in Korea. Actually, the left so the right part is data, and so the left part shows the AI and the 6G. And so we need some of the solutions on how to install some of the base station in underwater. Actually, it's not easy. And so nowadays, one of the solutions is to install just the gateway in the surface of the sea or some water. But however, in order to support the sustainability of the communication in underwater, for supporting 6G communication, and so we need the kinds of the flying base station and so the floating base station. In some cases, we need to have some assistance from the satellite communication, and then the AI. So by using the AI, we have to build some digital twin systems, as the Francois said. And then next one shows the standardization. Already you've seen this one from the video clips from the Francois. And so this one, yes, we have already the 6th standardization for the first time in the world for some of the public standard. Actually, we have another standards. That is a de facto standard. That is called the Janus, or some the Janus. The standard is from the EU and the United States, as I know. And then, it's time. But however, this published standard is for some public standard, ISO, ISD. And then we have the 5 ongoing project. This is the page, as this is me, and so this is domestic. And this page shows our roadmap for the standardization for the underwater communication of the underwater IoT. Yes, briefly to summarize what we talked, what we've done, and what we have to do. Yes, so here